everyone. Hello. Thank you very loud. Thank you so much for coming to my talk. My name is Colleen Schnettler, and I am a Ruby on Rails developer and consultant. You can find me on Twitter as Leanieburger. I run a Rails consultancy called Bitmap Designs. Pro tip, don't name your consultancy Bitmap Designs, because no one can spell that. And today I want to talk to you about energy and happiness and creation. We're also going to talk a little bit about electronics and family. So I'm going to attempt to cover the entire human emotional spectrum, so wish me luck. So I want everyone to think back. Think back about when you got into software development, whether it was 6 months ago or 20 years ago. What brought you into software development? Like, really take a minute and just think about it. So I have been thinking about this question recently, and some things came to mind for me, such as like creating something, more ambitious things like changing the world, having control over my own destiny and my own career. And of course, making money was always important to me as well. But I think the main reason I got into engineering was because I really love math. And I've always loved math. I was really good at it, and I was going to be a math major. But I discovered engineering, and I decided to become an engineer because I realized it seemed to be a better way to kind of mold physics and math and like practicality and actually build something. So I went to Purdue University, and I studied electrical engineering, and I had a wonderful 4 years at university. And, it was this amazing culture of like really believing we could change the world. We were learning the skills that were going to impact people all over the world. And because we were software engineers, like the things we do have a direct impact on mankind. So I graduated college with all of my idealism and ambition, and I got what was at the time my dream job, and that was a job at NASA in the robotics laboratory. So I was working in the robotics laboratory on actually the motors. This is Robonaut, which is a robot, and I was working in the lab on the motors that controlled the fingers. And this was like a really exciting, fun place to be, very research-focused. But, there was this disconnect between what I thought I would be doing as an engineer and what I was actually doing at a very large organization. And so one of the reasons I really got into engineering was that scene in Apollo 13, the Tom Hanks movie. There's this scene where the guys are up, about to die, and they get the engineers in a room, and they're like, you have to make this square peg fit into this round hole with this duct tape. Whatever it is, I don't remember the details, but it was something like that. Like, you have this time-constrained, really exciting thing, and it's going to directly impact like the future. And so that's the kind of thing I thought I'd be doing as an engineer, like solving problems and publishing that stuff and like putting that stuff out in the world. And the thing about working for a very large organization was I was unprepared for the level of bureaucracy. And to be fair, I was there at a very bad time because Columbia had crashed within a few years. So there was just a lot of meetings, lots and lots of meetings. And decision-making was very slow. And it felt like, as someone who wanted to build something and like was excited, it felt very, very challenging to really make any progress, because you'd do something, you'd have a great idea, and you'd have to like have 5 meetings, to even get an okay, you can try doing that. So, like, my enthusiasm and like my idealism just kind of dimmed a little bit during my time there. So let's fast forward to today, like 15 years later. I'm sure, like many of you, my career has taken many twists and many turns, but now I'm a consultant, as I mentioned, and to me, I'm living my dream again. So my life has changed, and I have been able to find this career as a Rails developer that really fits well into my life. Like I'm doing something I love, I get to do it on my own time in a remote, flexible environment. It's great. But I noticed like about a year ago maybe, I was really having a hard time tapping into that energy I had when I was 22. And you know, maybe it's because I'm not 22, but I'd like to believe that that's not the only reason. You know, life is different now, and it's busier, and I have children. But man, I was just kind of feeling blah in work. And I missed that kind of like idealism, like that energy to really do something. Like hopefully at some point in your career or your life, you have been able to tap into like that energy of like the possibility of change. And I just wasn't feeling it. And I was really missing it. And I think part of it might just be the like daily monotony a little bit of work. And the frustration of meetings, like the annoyance of tech debt, or, you know, bad code, boring work, and everything else we have to do sometimes, you know, they call it work for a reason as engineers. So that got me thinking, why are so many software engineers dealing with burnout? And this is not a talk about burnout, but I think this is kind of relevant to our discussion today. So almost everyone I know in this field, after they've been in it for a couple years, has dealt with some kind of burnout. And it appears in different forms, but ultimately, I think one of the problems is a lack of enthusiasm, like a lack of creativity and this lack of ability to just do something for fun. In our field, we have all of this pressure to work all day and then to have a side project that we monetize and to have a blog and to have a YouTube channel or whatever it is. I feel like there's a lot of pressure in our industry to work beyond like kind of a normal working day. And, you know, so I do think some of that stress is self-created, but, you know, it is what it is. So I was trying to think of a fun way to like fight that and to rekindle that energy. And so I decided that I wanted to just create something for fun. No other reason. I'm not going to sell it. I'm not going to do YouTube tutorials on it. Like, it's just going to be something fun. Like, remember how to have fun? And so I threw it out to my kids. I have 3 children. They're 3, 6, and 8. And my 8-year-old has shown a real interest in robotics and programming. So I threw it out to my children. And my son was like, hey, let's build a robot. And I was like, sure, let's first get an LED blinking, then we'll talk about building a robot. But the cool thing about children, if you have children, you know this. If you know children, you know this. They have this like sense of like nothing is impossible. They just create things to create them without feeling the judgment we as adults feel. They just build things, they color things, they're terrible. They don't care, they just put it out in the world. And like that lack of fear of failure is so inspiring to me. So we decided we were going to first get an LED blinking, but eventually work up to a robot. And so that sounded like a really fun idea to me. I wanted to build it with a Pi. There are lots of amazing robotics kits out there. They're pretty expensive, some of them, and I'm kind of cheap, so I was like, I don't know if I want to do that. And I was really looking for like, I didn't want someone to tell me what to do. I really wanted to just do it however I wanted. And so that's kind of why we decided not to use a kit. Of course, there's nothing wrong with kits, but that's the approach we took. So if you want to get started with the Raspberry Pi, this talk is going to give you kind of a step-by-step guide to getting started with the Pi on Ruby. So here's some like practical considerations. I think when you're first starting, you don't even know where to start. Like you don't even know what you need. So you're going to need a Raspberry Pi. You can purchase those as a kit, or you can just purchase them without a kit. I have to say, like I bought one of the really starter kits, and it came with a switch, which you can't really see, but it has a switch on the power supply. And that's really nice because if you're working with kids, it's better than like having them unplug it and plug it in and, you know, electrocuting themselves. So if you're going to work with kids, I highly recommend the $5 switch. You're going to need an SD card. You're going to need like various jumper wires and things. They look like this. You can come see after. But like various jumper wires, resistors, LEDs. alligator to pin clips, and then the stepper motors. So if you want to make something that moves, stepper motors, and then some breadboards. And so you can buy all that stuff in a kit from Adafruit. You can go to your local, electronics store. However you want to assemble your things is fine. But this is like a pretty good place to start. And so the step one, if you want to get started, is you got to flash your SD card with Raspbian. If you are scared to flash your SD card, you can actually buy the SD cards with something called Noobs, N-O-O-B-S, so it's preloaded on the card. Or like I said, just buy an SD card and you can flash it with Raspbian, which is the OS for the Raspberry Pi. Then once you've done that, you've got to actually install Ruby on your Raspberry Pi. It comes several things come preloaded, one of them being Python, but Ruby does not. But it's just a computer. Like sometimes you forget, you're like, it's just a computer. So it's just the way you would install it on your own computer. And then I put this up here, don't get distracted by how cool Scratch is. If you have children, Scratch is like a visual programming language. And so we got this all set up, and like, I'm all excited to get to the electronics portion, and my kids found Scratch, and that's all they wanted to do was play with that. So that is really cool. Highly recommend. But we were trying to focus a little more on Ruby. So this is what the download page looks like for Raspbian to flash your SD card. All right, so step 2, so once you've purchased your stuff, you've flashed your SD card, step 2 would be, as I said, to install Ruby and make sure Ruby is working. And so this was like the first for loop we did. The first loop we did, I put all my kids' names in it and just ran it forever, and they thought that was really cool. And so I think they kind of started to see, like, there's this relationship between what I type in the computer and what it spits back out to me. So let's talk a little bit about what we're going to do next. So we are going to use electronics, and I'm going to give you a brief intro to electronics, just in case it's been a while or you've never learned it. So electronics, current flows in one direction. It flows from higher potential, the plus means higher potential, to lower potential. And a circuit is, you have to connect all of the conductive pieces so the electricity can flow. So this would be a short circuit, and that's bad. So if you connect, as you can see here, now your battery, it's like how you're not supposed to connect the battery terminals to each other, right? Because it'll melt your battery. So that's a short circuit. So when you're working with circuitry, you kind of want to make sure you always have something in line in your circuit so you don't accidentally create a short circuit and a mini fire. So breadboard. So what is a breadboard? I have my one breadboard hooked up here. Kind of looks like that. I'll show you on the next slide. So breadboards. So they're called breadboards because before we had physical breadboards, people used to take wooden breadboards that looked like that and like tape their circuits down to create circuits. So that's where the name comes from. But in electronics, this is what it looks like. It's called a solderless breadboard. And it's called a solderless breadboard because the connections are made without soldering. And the way these work is you have a power rail, which is this red rail right here, red, and you have a ground rail, which is this blue rail. And as you can see, so this picture is what you see from the front, and if you took the back off of your breadboard, this is what you would see. And these are electrical connections. So you have power, which goes this way, ground, which goes this way, and then you have all of your other connections, which are going this way. And that is really nice, because that way you can take your Pi, you can plug power in here, and then you have that power available anywhere on that rail to work with your circuit. So that's a breadboard. So let's talk a little bit about LEDs. I'm sure you're familiar with the term LED. LED stands for light emitting diode. And the reason I told you which way current can flow is because in an LED, current can only flow in one direction. So current flows from plus to minus, the way the arrow is pointing. That's the way current flows. So the positive terminal is called the anode, and the negative terminal is called the cathode. And for the LED to work properly, you have to put it in the right way. If you put it in the wrong way, don't worry about it, just flip it around. Like, it's not going to explode or anything. But if it's not working, try flipping it around. So there's one thing that's missing. If we're going to hook up an LED, there's still one thing that's missing in our circuit. and that's a resistor. And so a resistor is a device that resists the flow of current. So practically, what does that mean? Basically, you are using your resistor to control the current in your circuit. And that's important because devices have certain current ratings that they should not be exceeding. So this is Ohm's law, and voltage equals current times resistance. So that is actually how you can go about calculating the size of your resistor. Here's an example of the circuit we're going to be creating, which is our current limiting resistor, our LED, and our power source. It's important to know on the Pi that you can get 3.3 or 5 volts. So just be aware of which pin you're using, because some are 5 and some are 3.3. So this is how you calculate the value of the resistor. And this is like if you're interested in circuits and math. If you're not interested, don't worry about it. It's not that important. But the way this works is you have your source voltage, which is Vs, which is coming from your Raspberry Pi. You have your forward voltage over your LED. So you subtract that, and then you divide by what you want your forward current to be. Now, how do you know what you want your forward current to be? You know because your LED is rated for a specific current. So the truth is, like, it doesn't really matter. Just grab a resistor. If it starts smoking, like you picked the wrong one, and grab another one. That's how we do it practically. So that's kind of my like brief introductions to circuitry and circuits. This is what the Raspberry Pi pinout actually looks like. And the way we identify pins is we go across and down. So it looks like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way down the board. And there are 2 different ways to identify pinouts. I mean, this is the way I learned 15 years ago, so this is the way I'm going to do it. So that's how you know what pin provides what voltage and whether it's an input pin or not. So now that we know all about circuits and we have kind of an idea of how to hook it up, let's go back to our circuit diagram one more time. So we're going to hook our LED up in series. This is called series because they're right next to each other with our resistor and power supply. So to do this, if we just did this, that would turn on our LED. We want to blink our LED. So to blink our LED, we have to control something else in this circuit. And what we're going to control is we're going to control this voltage right here. And the way we're going to do that is to use something called the GPIO pins. So if we go back to our pinout, you can see there's several of these that are labeled GPIO, GPIO, GPIO. That stands for General Purpose Input Output. That means the pins can be used for input or output. And those pins are tied to the 3.3 volt rail, so when they provide output, they will provide 3.3 volts. So we're going to blink an LED. So this is kind of what your circuit looks like, and I have it set up here. I know you can't see it, but you can take a look after the talk if you like. But you're completing your circuit, and what they have, and in this diagram, it's ground to your resistor, to your LED, to GPIO. So you can see that this is ground, and this is the GPIO we're going to control. So by switching that GPIO high and low, we're going to provide power to our LED, then we're going to turn it off, then we're going to provide power, and that will make our LED blink. So to control the GPIO, I used a Ruby library called RPI GPIO. And like as an aside, if you've used the Pi, you've probably used Python on the Pi. Python comes preloaded, very popular, and Python has a lot of libraries that kind of abstract all of this. They probably have like a Blink LED library. Like they just abstract all of this away. So I really think there's like a fun benefit to learning how to control the GPIOs on your own, because you can really understand the circuitry and really understand what it's doing, but it is a little bit more work. So this is the, oh, you can't see that so well. Sorry about the red. This is the code I wrote. And basically with this particular library, and there are other libraries, you have to set the numbering. So as I said, we're going to go with the board numbering, which is kind of the more traditional numbering scheme. So I just set up pin 12 as output, initialized it low, and then I set it high, sleep, set it low, sleep, and it blinks. So hopefully you've made it that far, and you're still interested, and you're still having fun with circuits. And You're blinking an LED. Yay. So let's talk about the second project. And like I said, I do have these projects set up so we can, you can always take a look after the talk. All right, so let's talk about project 2, which was a whoopee cushion, which is this. It's connected to my Pi right now, but I'll try to hold it up. This beautiful device is my whoopee cushion. And this was fun because this was really, the LED, the kids weren't too excited about that. But the whoopee cushion, everyone was excited about. And if you look at this, as I show you how I made it, you'll see that it's really just a really big button. So what you need, 2 paper plates. I recommend Chinet, so they expand a little better and they don't just fall in on each other and keep your button pressed the whole time. Alligator clips. Aluminum foil, that's what we use for our conductive surface, is aluminum foil. So if I take this apart, you'll see it has aluminum foil in the middle. And then you can put sponges around the rim here to give it more bounce. We tried that and we didn't really find it to be too effective. So you're going to connect one LED. So as you see, I have conductive surface, and then you can see there's a conductive surface coming out right here, conductive surface. So when you put it together, don't put the conductive surfaces going out together. That won't work. So you have to put the conductive surfaces not touching, and then you hook up alligator clips, and it just makes a really big button. And so when someone sits on it or you depress it, your 2 surfaces are going to touch, and you're going to close the circuit. And this is the code I used. Yeah, I have a folder now called farts. And so set up pin 18 as input. I pulled it up. So there's 2 ways to do it. You can start with it low and pull it high, or you can start with it high and pull it low. So it was just because I was doing this all on the same Pi, so those were the only pins I had available. So you can just pull it up, and then you have your farts. And then, when the pin goes low, you play a fart sound. And so this was really fun. One of the things that's interesting here that sometimes I think as software developers we forget is you have to wait. Because you're responding to a physical event. It's not what we're used to. So when I first coded this up, I didn't have any sleep in there, and it was not syncing up properly, and I couldn't figure it out. It took a while. But you have to remember, hardware is slower than we're used to. So you've got to keep that in mind as you're making this. And hopefully this... That's hard to hear. It's coming out. Oh, well, it makes a good fart sound. So that was a very popular project in my house. All right, so I'd like to talk to you about the third project we worked on. So if you are doing this with children or even yourself, let's talk about managing expectations. Because kids these days have robots at their house, they have robots at their school. We went to the library, and our library has this robot, just because they're awesome, and you get an iPad, and you just move your finger around, and the robot follows your finger. It's amazing. So we go, and my son's like, can we build that? I was like, not today, maybe someday. But I think one of the cool things about this project, it really kind of gave my kids some perspective on things are hard. These robots are built by teams and teams of people. So, it's interesting what you can do at home. So I would just recommend managing expectations when you go into that. Ours will pale a little bit in comparison to what your children might be used to seeing at school. So, robot, you got to be able to move. So the biggest thing with movement is motors. So I used a stepper motor. Stepper motors are a little bit different than what you think of as more your traditional DC motors, because you can program them to move in tiny increments. And the reason we chose to use a stepper motor is because they were $6. And I really didn't know how this was going to turn out when we started this. So they're super cheap. They come with their own driver board. So that's the driver board, and they come packaged together. And it gives you really precise control. And I had no idea what we were going to be doing for the physical yet, so I didn't know if we'd have an axle connecting the 2 wheels. So I thought it was important to get precise control so our robot wasn't, going off in all different directions. So that's why I used a stepper motor. And so I want to talk to you a little bit about stepping. So motors, brief description of motors, they have a magnetic core, and then you are sending an electric current through a coil, and when you send an electric current through a coil, you create a magnetic field. That's what causes motors to turn. So if you look at this, hopefully this works. This animation, which unfortunately isn't working at the moment. There we go. So if you look at this animation, you can see in this animation how a coil is exercised. Okay, I don't know why we call it exercised, but we call it exercised when you send a current through it. A coil is exercised, it creates a magnetic field, and your permanent magnet in the middle turns, right? Because magnets are attracted. And if you look over here, you can actually see the stepping sequence. This is called half stepping. There's a few different ways to do your stepping, but basically in half stepping, you turn one on, and then you turn two on, and then you turn one on. Let's see if I can get it to play again. Oops. And then you turn one on, and you turn two on. So if you look over here, you can see high, low, 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 and then you have high, high, low, low. So you can kind of see the pattern, if you look over here, of how to do half stepping. And so what that pattern actually looks like, oh, now it's going to play again. Okay, you can watch it again. So red means it's on. So now you have two on, now you have A prime on, now you have A prime on and B prime on, B prime on, B prime and A on. Okay, so this is what that sequence actually looks like if you were to put it in an array. So just like we just saw in the physical diagram on the last slide, it's 1, 1, 1, 0, 1, 0, 0, then 2 on, then this one on, then these two on, and you just go in that sequence, and that is going to cause your stepper motor to turn. And each of these four values correspond to a specific pin on your stepper motor. That's important. So your stepper motor, when you connect it, it has 4 pins, and each of these is going to correspond to a specific pin. So let's look at how this works. So my suggestion when you get this up and running is to first try to get one motor spinning, and then once you have one motor spinning, you can try to get 2 motors spinning. So here's what an initialized method might look like for 2 motors. So what we have here is I have control pin and control pin 2 because I have 2 motors. And these are just GPIO pins that we were talking about earlier. These are our GPIO pins. And we have 8 of them total because we have 4 per motor. And we're just going to set those pins up as output pins, initialize low. And they need to be output because we're driving the motors from the Pi. So if you think of the way like you're kind of sending, you're coming from the Pi to your motor. And so you're going to set them up, you're going to initialize them low. And, okay, so 2 motors, 4 pins. So what we're looking at here is we have, for pin 0 to 3, set pin. So here's kind of like some pseudocode for set pin. And this basically is going to take a pin and a value and set the pin to the value. So, and as I said, we have 4 pins. And as you see, we have half step, 0, oh yeah, here's a reminder of our sequence, of what our sequence looked like, what our sequence array looked like. And here's our half-step sequence again, and there's 8. So if you look back at this, you can see we're doing 4 half-step, 0 to 7, 4 pin in 0 to 3, and we're going to set each one of those pins. And to sleep, again with the sleeping, we don't want to forget the sleeping, because we are moving a physical device, so we have to wait a little bit of time to make sure the physical device can move. Okay, so here is what go forward looks like for me. And to make one complete revolution, I have to go 512 steps with half stepping. And that is going to be determined based on your motor, and that will be spec'd out in your motor, so you should be able to find that information. And so this is my go forward method. We go 0 to 5, 11, and then we do our half steps, and then we set each pin as we go through the loop. All right, so now we have, like, if you think of where we are, like we have motors that are spinning, which is cool, and we were trying to figure out how to put this in a physical device. And at first we started with Legos, and I'm sure there's a great way to do it with Legos, but I wanted to glue the stepper motors to the Legos, and my son was not having that. So there was no gluing of Legos. So the Legos didn't really work because I was having trouble like figuring out how to get the stepper motor attached to the Legos. But we discovered Thingiverse, and this is a super technical crowd, so probably half of you have your own 3D printers, which would be awesome. We do not. I have never used a 3D printer in my life, and I discovered Thingiverse, and it turns out my local library has a 3D printer. So we got a design, and we didn't design this ourselves. That's like step 2 of our process. I'd love to learn how to do it, but we did not have time for that. So we got a design, and we printed it at the library for $3. It was amazing. And so that was really, really exciting for everyone. And this is our robot, as you can see, right here. And we hopefully this will play, and it goes, get ready. This is very overwhelming. Look how fast it goes. And you'll notice, like, this is kind of funny because you'll notice I still have it plugged in. So I was running it off this battery pack here, but it was just destroying the battery, and it's an old battery pack, and I probably should have sprung for a new one. So, you know, it's not exactly an overwhelmingly amazing experience, but we built something ourselves that moved, and we were really excited, and the kids were really excited, and it just felt fun. And so I think that's really cool, and I hope you learned a little bit about electronics and a little bit about the Raspberry Pi, but like my goal was not necessarily to teach you how to build a robot, although I'd love to talk about that. My goal of this talk was just to like remind you how to have fun and remind you that at our heart, most of us are creators, and sometimes throughout the course of our lives and our days and our adult responsibilities, like we forget to have fun and just create things. So if you're looking for a fun project, the Raspberry Pi is a really great device to get you up and started cheaply and quickly, and you can create new things. Thank you very much.